Welcome to Your Math Explained, where we make math simple and clear. My name is Angela. In our last video, we broke the habit of always isolating y first before differentiation. We learned that we can find the slope of a curve even when x and y are tangled in a chaotic mess. Today, we're going to go further along that line of exploration. What if we need to know the curvature of that mess? That means we need to find the second derivative. And what if we use implicit differentiation not just to solve equations, but to invent new formulas, like the derivatives of arcsin x or arctan x? Today, we move from just finding slopes to uncovering the second-order behavior of curves and the secrets of inverse functions. Now, before we get started, if you haven't subscribed to the channel yet, make sure you do that first so you don't miss out on new weekly content. For our first example, we want to show that the second derivative of the equation of this circle that we looked at in our last video is negative 25 over y cubed. So of course, in order to find the second derivative, we have to take the first derivative. And we're going to do that through implicit differentiation. So that means we take the derivative with respect to x on both sides of this equation. So we get d by dx of x squared plus y squared is equal to d by dx of 25, which means we get 2x plus 2y times dy dx is equal to 0. And now we can go ahead and isolate our dy dx. So we end up with dy dx is equal to negative x over y. So this is our first derivative. Now to find the second derivative, we just need to take the derivative with respect to x again, which means we're going to go d by dx of dy dx is equal to d by dx of negative x over y. So the left-hand side, that is what we're looking for. This is the second derivative, which is d squared y over dx squared. And then now the right-hand side, we're going to have to use our quotient rule. So let's go ahead and factor out the negative to the front. And then we get the derivative of x, which is 1, multiplied by y, minus x times the derivative of y, which is dy dx. And then this is going to be over our denominator squared. So that'll be divided by y squared. So notice how here we have dy dx in our expression. So what we need to do is we need to substitute negative x over y into dy dx, which means we get this is equal to negative y minus x times negative x over y squared. And now let's go ahead and simplify our numerator. So we get this is negative, and then we're going to need to put our numerator over a common denominator. So we're going to put both terms over y, which ends up being y squared over y plus x squared over y. And then we can actually just combine that y with the y squared on the bottom to get y cubed. And now the final part is our numerator is x squared plus y squared. But notice that x squared plus y squared is just 25. So again, we can do another substitution here, which means our final answer is going to be negative 25 over y cubed. And that is exactly what we're trying to show. Now let's take a look at how implicit differentiation can help us find the derivative of some inverse functions. First, suppose that f is a one-to-one function, and its inverse function, f inverse, is also differentiable. Then, the derivative of f inverse of x is equal to 1 over the derivative of f inverse of x. And of course, this is provided that the denominator is not equal to 0. And this can be proved quite easily with implicit differentiation. So let's go ahead and take a look at the proof. What we're going to do is we're going to let y be equal to f inverse of x. Then by the definition of an inverse function, f of y is going to be equal to f of f inverse of x, which is equal to x. And now we're going to take the derivative of both sides of this equation with respect to x. So we go d by dx of f of y is equal to d by dx of x. Now the left-hand side, we're going to get df by dx of y, and then chain rule says we need to multiply this by dy dx, and then the right-hand side is just going to be 1. And then isolating dy dx is going to give us dy dx is equal to 1 over df dx of y. Now notice that df dx of y, this is just f prime of y. And that dy dx is just y prime. But remember, we set y to be equal to f inverse of x, which means this is just equal to the derivative of f inverse of x. So therefore, substituting all of these in, we end up with the left-hand side is the derivative of f inverse of x is equal to 1 over f prime of y. And now we just have one last substitution to do, which is this one right here, where y is equal to f inverse of x. So which means finally we get the derivative of f inverse of x is equal to 1 over f prime of f inverse of x. And that is exactly what this is. And so therefore, we have completed our proof. Next, let's take a look at how we can use implicit differentiation and inverse functions to derive the derivative of arcsin of x. So to do that, we're going to let x be equal to sine y. And this means that y is equal to arcsin of x. So then we're going to start here, and then we're going to take the derivative with respect to x on both sides of this equation. So then we get d by dx of x is equal to d by dx of sine y. Now the left-hand side, that's equal to 1. And then the right-hand side, we'll have to use our chain rule. So the derivative of sine y is going to be cosine y. And then we're going to multiply this by the derivative of y. So that's going to be dy dx. So notice that y is equal to arcsin of x, and we're trying to show that the derivative of arcsin of x is equal to this expression here. So really what we're looking for is what is dy dx. So which means we're going to isolate our dy dx here. So then we get dy dx is equal to 1 over cosine of y. So now we just need to relate this to this. And there are a couple of different ways of doing this. The way that I'm going to show you is using a right angle triangle. So if we have a right angle triangle, now notice that we have x is equal to sine y. So that means if we have our right angle triangle here, and then let's call this angle y, sine y is equal to x, which means that opposite over hypotenuse is going to be equal to x. And the simplest way to do that is to name the opposite side x, and then name the hypotenuse 1. Then this triangle satisfies that sine y is equal to x over 1. But because this is a right angle triangle and we have two sides already, we can use that to find out what the last side is using our Pythagorean theorem. So by doing that, we get that this last side here is going to be the square root of 1 minus x squared. So now, if we want to find what cosine of y is, cosine of y is going to be adjacent over hypotenuse. So in this case, our adjacent side is the square root of 1 minus x squared, and then our hypotenuse is 1, which means we end up with this is equal to 1 over the square root of 1 minus x squared over 1, which we don't need to write down. And again, the left-hand side is dy dx, and since our y is arcsin of x, that is really just the derivative with respect to x of arcsin of x. And thus, we have shown that equation to be true. And similarly, the derivatives of arccos and arctan can also be found that way. And for simplicity's sake, we have written down the derivatives of all the inverse trig functions on the screen here. Feel free to verify the derivatives of arccos and arctan on your own if you wish. And now for our last example in this video, we want to find the derivative of arctan of e to the power of 2x. So here, we're going to have to use chain rule. Our inside function here is e to the power of 2x. So if we were to do a substitution here and we say that u is equal to our inside function, which is e to the power of 2x, then the derivative with respect to x of arctan of u is going to be equal to 1 over 1 plus u squared. And then we multiply it by the derivative of u with respect to x. So which means here we're going to have f prime of x is equal to 1 over 1 plus e to the power of 2x squared. And then we multiply this by the derivative with respect to x of e to the power of 2x. And this part, this is going to be equal to e to the power of 2x times the derivative of 2x, so times 2. So that means our final answer here is going to be 2 times e to the power of 2x over 1 plus e to the power of 4x. And now let's go ahead and do a quick recap of what we covered in this video. We saw that when we're trying to find the second derivative implicitly, the expression is going to contain the first derivative, which means we have to substitute our result for the first derivative back into this expression and then simplify so that our final answer is only in terms of x and y and no y prime. We learned how to find the derivative of inverse functions using implicit differentiation and how that came into play when we want to find the derivative of our inverse trig functions. One additional piece of information that was needed there was the use of reference angles in order to convert trigonometric terms back into algebraic expressions. And now it is your turn to give this a try. Can you find the second derivative of the equation on the screen here? Make sure to leave your answer in the comments below and let us know what other calculus topics you'd like to see in the future. That's it for this video. If you found it helpful, remember to hit that like and subscribe. And if there's a topic you'd like us to cover, make sure to drop it in the comments.